Today's lesson is math with significant figures. The learning target is I can maintain precision when making calculations. So, actually, let me fix this while I'm talking to you. Let's imagine that I am trying to find the area of a sheet of aluminum foil. Okay. We'll say my length is this 1.2 centimeters right here, and my width is 4.8 centimeters. Okay. When I put this in the calculator, I do length times width. I'm going to wind up getting this 5.76 centimeters squared. In doing this, my calculations gave me some extra digits. And when I get these extra digits, here I'm going from, two significant figures, two to significant figures, all the way over to three. This is going to cause a problem because what happens is that my measurements, just by doing math, look like they're more precise than they actually are. It makes me look like my tools got better after I did the math. If I am getting 1.2 centimeters, this means that I got 1.2 centimeters. I'm going out one decimal place. Now I'm going out two decimal places. That's adding precision, and I only added this precision by doing the math. I got an extra digit, and that is not allowed. If I were writing up a really good chemical journal and people were going to read it all over the world, Japan, Brazil, France, Germany, Australia, wherever these people are going to read it, they're going to think that I'm measuring with really precise equipment because as I'm doing math, I'm getting more significant figures, but that's not really true. So it's almost kind of like lying. So, how we fix this issue, scientists have made some rules so that we don't accidentally add precision just by doing math. And essentially, these rules are going to tell you how to round your final answer. So, depending on the operation that we're doing, we need to change how we're rounding these numbers. And it just comes from the nature of addition, subtraction, multiplication, division. So when I'm adding or subtracting, my job is to focus on the number of decimal places in each number. And then my final answer, needs to have equal precision to the measurement that had the least precision. Okay. That sounds a little crazy, a little scary, but it makes sense with examples. Okay. So just hang with me. Addition and subtraction, stick to your decimal places. If I were to add the number 5.4321 to 1.0, this is what would come out in the calculator. Okay. I am taking a number with one decimal place, and all of a sudden I'm getting a bunch more decimal places just by doing math. That's not cool. So the rule says that my final answer should match or have the same number of decimal places as my measurement with the fewest number of decimal places. In that case, this 6.4321 needs to be rounded so that it only has one number after the decimal. That's how I get 6.4. That's addition. Subtraction is the exact same way. If I had 6.8 and I was subtracting 1.234567, the number I would actually get is 5.565433. Okay? I need my final answer to have the same number of decimal places as my measurement with the fewest number of decimal places, which is 6.8. That has one number after the decimal. That means my answer should have one number after the decimal. So I'm going to take this 5.565433 and I'm going to round it so that I only have one number after the decimal. This 6 kicks the 5 up because it's a big number, kicks it up. So 5.565 whatever becomes 5.6. Okay? You with me so far? If not, back it up and watch again. Here we go. Multiplication and division. When we're multiplying or dividing, we, instead of focusing on decimal places, here we're focusing on the number of significant figures. Again, we want our answer to match the measurement with the least precision or the fewest number of significant figures. Okay, so example, I'm taking 52.8 and I'm dividing it by 3.8. When I put this in the calculator, I get this seemingly never-ending number. Okay, this adds a ridiculous amount of precision to my answer, even though I'm only measuring things with decently low precision. So here, 52.8 has 3 sig figs. 3.8 has 2. 2 is smaller than 3. So these 2 sig figs should be reflected in my answer. So my final answer is going to get rounded so that I just have my 2 sig figs. So 13.8947 blah, blah, blah gets rounded up to 14. Rounding it down to 13 mathematically is not correct. So 13.89 gets rounded up to 14. And then I have 2 sig figs. You can put a decimal behind it. You can skip the decimal. Technically, it doesn't matter. But you should not round your answers until the very end. Just a heads up. Okay, here I have 8.4 times 9.60. I have 2 sig figs here, 3 right here, turning into 4. Not cool. My final answer needs to match the least precise measurement, which is 8.4. This only has 2 sig figs. My final answer must also have 2 sig figs. So my 80.64 gets rounded up to 81. Okay. If you are lost, pause. Do not continue. If you are lost, this next thing is going to break your brain. And I don't want to break your brain. Okay? So if you're lost, go back, rewatch, listen again. If you're with me, let's roll. Okay. You can see here that in 2 different ways, I'm getting 50 divided by 2, and I'm getting both 25 and 30 as my answers. Okay? I'm going to explain why this is kind of funky. All right? This is 50. Imagine we're measuring volume. Okay? We're going to measure volume in a graduated cylinder. Just picture it. The graduated cylinders we have in our classroom count by ones. There's a line for every 1. They only write the number for every 10 so that it doesn't get cluttered full of numbers. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then they write 10. And then you're supposed to count between 0 and 10 to figure out what specifically it is, right? So let's imagine all of the little lines on that graduated cylinder were gone. It was just 0, 10, 20, 30, 40, 50, 60, 70, etc. This measurement would come from a graduated cylinder that measured by tens, because it's telling me that this is the 5, the known digit, and this is our 1 estimated digit. With me? If you have a ruler, find a ruler and look at it. Look at the centimeter side. A typical ruler is around 30 centimeters. Okay? Imagine taking out all the numbers 1 through 9, 11 to 19, and 21 to 29, and only having the numbers 0, 10, 20, 30. That would be a really crappy ruler. It would not measure anything very well. This measurement came from a piece of equipment like that. That's why we're getting this crappy answer. 50 divided by 2, excuse me, 50 divided by 2 technically is 25. That's why we're getting 25. But when we get 25, we're adding precision to our answer because this number only has 1 significant figure. So my answer should have 1 significant figure. 25 needs to round to 30 in order to get 1 sig fig. This is a junky measurement, and that's going to give us a junky answer. Okay? That's why this comes out completely wrong. Even though technically, according to the rules of significant figures, it is correct. If you did this in math class, your teacher would be disappointed. If you did it in science class, your teacher would give you a major high five because a lot of kids get this idea wrong. A lot of kids have a hard time envisioning it because it's kind of silly. 50 divided by 2 is not 30. It really depends on how that 50 and how that 2 are written. So here you can see that we're getting the correct answer, and that's because we have really good precision here. This graduated cylinder would be measuring by ones. Remember, you have to give one estimated digit. This tenths place is the estimated digit. So this is measuring by ones, add in one more digit for your estimated digit. This is a good graduated cylinder. That's why we're getting a good answer. So we're still dividing by 2.0 in both situations, but here we're going up to 3 sig figs. Here we're going by 2. We need to have our answer match the fewest number of significant figures. So this is our fewest. 2 is fewer than 3. So our answer should have 2 significant figures to match, giving us the proper answer of 25. The better your measurement, the better your tool, the more accurate your answers are going to be. It's that simple. So I'm sorry if I broke your brain by doing this, but it was really to get you to realize, which something that you already knew, the better tool you have, the better measurements you have, the better measurements, the more accurate you are, et cetera, et cetera. You knew all of this. I just put it in science language for you. Okay. If this part is confusing, it's not the end of the world. If this is confusing, and if this is confusing,